Welcome to today's technical science lesson. My name is Mashidu Mamboro. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. As indicated, we are doing technical science paper 2. Organic chemistry will be our focus because paper 2 is the paper that I think you must spend more time on because majority of learners are not doing well when it comes to paper 2. So I will encourage you to go with me and ensure that you do well in paper 2. There are a lot of marks and it's not a difficult topic. These two topics that we do as indicated here, we have matter and materials, we have chemical change. Under matter and materials, we are doing your question 2, which is basically naming of organic molecules, your physical properties, and then your reactions, as well as electronic properties of matter. That's where your 47 marks will come from. That the weighting of that is 62% of the paper. So if you do very well in this organic, you'll be able to pass this paper because our paper is 75 marks and of which 47 are from organic chemistry. You are writing as you saw during your prelim for 1.5 hours. So I'm hoping we'll spend time and then ensure that you understand. As I've talked about the section already, we are focusing on the module 1. In this case, it's naming of organic molecules and isomers, physical properties and reactions of organic molecules. Now, I wanted just to start with this multiple choice question to say which one of the following homologous series has a carbonyl group as a functional group. So the emphasis here is that you must know the functional group, the names of the functional groups to say what is the name of a functional group for each homologous series. Remember, it's the 9 homologous series that we are doing. So we're saying for each homologous series, know the functional group. And some of these functional group, like a carbonyl, they are named as carbonyl group. You have others named as formyl group, hydroxyl group, carboxyl group, and all that. So know the names of each of those homologous series, because if you look at this question, it's based on that to say which one of the following homologous series has a carbonyl group. So majority of learners, they think that every structure that has a C double bond O like that will be referred to as a carbonyl, of which most of the time you'll find that you are not correct. Look at the first one, or option A there. We are given haloalkanes. So this one strictly, you know, haloalkanes are those group 17 elements. For text science, we only focus on bromo and chloro. So you will know that this cannot be a carbonyl group because we are having the halogens. So that cannot be the answer. So A is not the correct answer. When you go to B, it's saying aldehydes. And if you check aldehydes, they have a C double bond O, but that C double bond O is bonded to a hydrogen. Now that becomes a disruptor or distractor to you, because what you are looking at there is the C double bond O, and then learners make a mistake of identifying C double bond O there, and then without checking that the C double bond O is attached to a hydrogen, and that group will refer to it as a formyl group. So aldehyde, the group is formyl group. So that cannot be the correct answer because for aldehyde, the group is referred to as formyl group. Let's look at our next option, which is option number C, where we've been given an alcohol. Now, when it comes to alcohols, you will have an understanding to say for alcohols, we are having OH, which is our hydroxyl group. So this one is hydroxyl group. So you have to know that for alcohols, we have hydroxyl group. So it cannot be a carbonyl. You are only left with one option, which is option number D, a ketone. A ketone is a C double bond O that is bonded to 2 carbons. So please understand that it's a C double bond O bonded to 2 carbons. It's referred to as a carbonyl group. So you must know that a carbonyl group will be for ketones. But for aldehydes, it will be formyl group. So don't confuse the two. So our correct answer there will be option number D. And it's very much important to spend some time. Remember, you have 2 minutes minimum to spend on each multiple choice question because you have 2 marks there. So please spend that 2 minutes, check all the options. Don't just guess the correct answer. So you're able to choose D there as your correct answer. And then as we move forward, we are able now to move to 1.2. Which in 1.2 we're saying consider the structural formula of the alcohols given. So the alcohols that are given in Roman figure 1, we're having an alcohol. Remember, what makes an alcohol is its functional group. In this case, our functional group is the OH. So that OH, which is the hydroxyl group, is the one that makes the structure a functional group. I most of the time would like to advise learners to say, how do I know a functional group? Is that which, when you remove from the structure, it will remain with carbons and hydrogens only. So if you remove OH there, you can see that the structure now is it will be like an alkane. So the functional group is OH group there bonded to the carbon. Remember, if we say write down the functional group, you will indicate that it's the OH, but that OH must be bonded to the carbon. So you are able, the carbon is important there as you write the functional group. But what is the name? We said is the hydroxyl group. For OH, we said the name is hydroxyl group. So don't forget that. Now, if you look in the first option there, which is Roman figure 1, we're having OH in this position. So let's look at Roman figure 2, the OH is in that position. Roman figure 3, the OH is in that position. Roman figure 4, then the OH or the hydroxyl group is in that position. So we define an alcohol based on the position of the hydroxyl group or of the functional group. So we're looking for a primary alcohol. By definition, a primary alcohol will be the alcohol where the hydroxyl group, the functional group, the OH, is bonded to the carbon that is bonded to the OH is bonded to one other carbon or one other hydrogen. In this case, if we look at Roman figure 1, you are having the OH, but the carbon, we are interested on the carbon that is bonded to the OH. The carbon that is bonded to the OH there is bonded to two other carbons. So there are two carbons, it's surrounded by two carbons around it. So that must be secondary. Because of that, is the carbon that is bonded to the hydroxyl group is bonded to two other carbons. Then we'll refer to that as a secondary alcohol. Now let's look at Roman figure 2. The carbon that is bonded to the OH or to the hydroxyl group is bonded to one other carbon. Then we'll refer to that as our primary alcohol. When you look at Roman figure 3 there, we're having our OH or our hydroxyl group, which is bonded to this carbon, is bonded to hydrogen. So that would be as well fit to be referred to as a primary alcohol. When you look at Roman figure 4, the last option there, we're having the carbon that is bonded to the hydroxyl group is bonded to three other carbons. So you can see surrounded by three other carbons. Then that makes it a tertiary alcohol. So you can see that Roman figure 1 and Roman figure 4, Roman figure 1 is secondary and then Roman figure 4 is tertiary alcohol. So those two options are out. We are only left with option where we have Roman figure 2, which is a primary alcohol, and Roman figure 3, which is a primary alcohol. So it's option 2 and 3. Option 2 and 3 becomes our correct options. Then you are able to choose your answer and then you are sure that you got it correct. Now, still to emphasize the issue of our physical properties, remember we have our physical properties, which is our third question, which in this case, you know, for technical science, we deal with the melting point, the boiling point, the vapor pressure, and viscosity. Now, one thing that we have to understand, because this question is based on viscosity, is saying a liquid with high viscosity. So the first thing is to understand that what is the meaning of high viscosity? High viscosity means that there is increase in the strength. There is a strong intermolecular forces. They are strong. If the intermolecular forces are strong, it means that it will have high viscosity, meaning that more energy will be required. So remember viscosity, we're talking about the resistance of a fluid to flow between the two adjacent, parallel adjacent layers. So we are saying now for viscosity, it must, for it to be to have high viscosity, it will mean we must have stronger intermolecular force. So let's look at our options that were given. A liquid with high viscosity, option number A, it says it will be faster because it has a high boiling point. I think you won't be agreeing with that, because you have to understand that if it has high viscosity, it has more resistance to flow, meaning that it can't flow faster. So option number 1 will be out. So we refer to it as a distractor. Let's look at option number B. It will flow faster again. You know that high viscosity means high resistance to flow, so it can't flow faster. So you know that option number A and B, our distractors, our focus now will be on option C and option D. For option D, we are saying it will flow slowly. It's always important to read it from here. To say it will flow slowly, you agree, because it has high resistance, it must be slowly. And even option D saying it must flow slowly. So in terms of flowing, it is slow, we are all agreeing. The second option, it says because it has a low boiling point. But you know that if it has stronger intermolecular force, the boiling point as well will be higher. So you are able now to say it cannot have a low boiling point, it must have a high boiling point. That makes option number C wrong. Now you are left with option D, that says it will flow slowly because it has stronger intermolecular force, and then you are able to get your 2 marks. I hope that helps you as you revise, as you prepare for your final exam, and you are able to collect as many marks as possible when it comes to this question of multiple choice. Now, once more, just to remind you what you have done as far as this topic is concerned. Remember, if you have the basic correct, you will be able to understand and enjoy the topic. What will make you not to enjoy the topic is when you don't have the background of why we are doing what we are doing. The first important thing when it comes to organic molecules, we are saying these are molecules containing carbon atom. So carbon is very much important, and one property of carbon is that it forms 4 bonds around it. So for example, when you have a methane, it will be carbon with 4 hydrogens, and we say that is our methane. So you are able to know that each carbon, all the time when you are drawing structural formulas, ensure that you have 4 bonds around each carbon. Now, these structures are referred to as hydrocarbons. Why? Because they contain only carbon atoms and hydrogen atoms. They are made up of hydrogens and carbons only. Don't forget to write the word only there. So you will say hydrocarbons contain hydrogens and carbon atoms only, because if you don't say only, your answer becomes wrong. So always remember that definition of a hydrocarbon. Now we're saying these hydrocarbons, they are either saturated or unsaturated. Now when you say they are saturated, I'm emphasizing the S there to say, remember, saturated will mean that they are single covalent bond between carbon atoms. So when it's saturated, it means there's no double bond, there's no multiple bonds between carbon atoms. For example, if we were to look at the structures I gave you here, this first structure there and the second structure there, they have single bonds between carbon atoms, and then you must ensure that your hydrogens are attached to the structure there, not that far from the carbon. Now, what happens now? We are saying saturated contain only single, so the S on the saturated will remind you that these are single covalent bond between carbon atoms. So it's another definition as well. So we're saying know what is hydrocarbons, and these hydrocarbons, they have saturated and unsaturated. If saturated, we are saying they contain single covalent bonds between carbon atoms. Definitely unsaturated will contain double or triple bonds, triple covalent bonds between carbon atoms. So there must be a double bond or a triple bond. So when you see a triple bond, you say unsaturated. When you see a single bond, you say saturated. Remember, here we said hydrocarbons, saturated ones is alkanes. Alkanes, and then all alkanes, they have one general formula, which is your CnH2n+2. we are always emphasizing that before you do anything, know the general formula of each homologous series, because as I indicated that you have 9 homologous series, and we're emphasizing that for all of them, you must know the general formula of each of them so that you don't have problems. Now, when you look at alkanes, for example, you will see that the general formula is CnH2n plus 2. So the N there, understand that the N stands for the number of carbons. So it's important, let's say N equals to 3, like we've given you here for propane. N equals to 3, you will go and replace, where there is N, you will write the 3, which stands for the number of carbons, which is C3H2. 2 times 3, you know it will give you 6. 6 plus 2, it will give you 8. So that will be C3H8. That will be C3H8, and then that will be your molecular formula. So you are able to move from general formula to molecular formula. And from molecular formula, you can draw all the bonds, which is in this case 3 carbons as we have drawn there, and 8 hydrogens around it. That's the structural formula. So look, the first formula, important formula we're talking about, is the general formula. After the general formula is the molecular formula. After molecular formula is the structural formula that we've indicated. Sometimes in the exams, we give you structures that are condensed. So it's important that you know that these structures can be condensed. And for the structure to be condensed, it will be CH3, or just saying on this first carbon, how many hydrogens we have. Then that will be CH3, CH2, CH3. Then you are able to know that that is a condensed structure. So it means in terms of formulas, you can know those 4 formulas that we talked about. The first one being the general formula. For alkanes, we said it's CnH2n plus 2, followed by the molecular formula, followed by the structural formula, and the condensed structural formula. Now, when it comes to unsaturated hydrocarbons, we're saying they contain covalent double or triple bonds. And in this case, for us to have a double bond, for example, if we are having a butane structure as given like that, if we need a double bond, we'll have to put a double bond. If we want to put it there in the middle, then we can put it there. But when we put the double bond there, we are going to have a problem that this carbon now will have 5 bonds around it. I think you can be able to count the bonds, 1, 2, 3, 4, 5. Then each carbon, we said, is tetravalent. Tetravalent means carbon has 4 valence electrons, so it can only form 4 bonds around it. So if you want to form a double bond, it will mean that you must remove hydrogen from each carbon where the double bond is. That's why in this case, you see we have a double bond here, but we no longer have the hydrogens there. Because when you introduce a double bond, you remove 2 hydrogens. Meaning that the general formula, from the general formula of alkanes, which was CnH2n plus 2, we're removing 2 hydrogens. Then the general formula for alkenes will become CnH2n. So you are able to know that now we have a new general formula, which is CnH2n. And we can follow the same steps. We can now go and say when n equals to 4, it will mean that you are going to replace, where there is n, you will write 4. So that will be C4, 2 times 4 is 8. So you will have C4H8. So you can see that for an alkane, it was C4H10. But for an alkene, it will be C4H8 because we have removed 2 hydrogens to accommodate the double bond. Please don't forget, it's very much important. So still for alkenes, you are able to move from general formula to molecular formula to structural formula. You can see that our double bond is in carbon number 2, but we can still be able to have a double bond into carbon number 1. So it means it has what? A positional isomer, because when you change the position of the functional group or the position of the double bond, it means now we have positional isomer. The name won't be the same. You can see we have named this one as but2ene, but if we move the double bond to the first carbon, we are now going to refer to it as but1ene. So you always indicate the position of the double bond only when there is an isomer. For example, if you have but2ene, it means you have but1ene. But if you were to write the structure of propene, you are not supposed to indicate the position of the double bond, because the double bond will remain in position number 1. So when it comes to alkenes, you only start to indicate the position from 4 carbons upward. So from butene, pentene, hexene, you will indicate whether the double bond is in carbon number 1 or number 2, depending on the structure that you are given. Now, if we were to move to alkynes, definitely to introduce another double bond, it will mean we remove another 2 hydrogens. That's why for alkynes now, we're going to have general formula of CnH2n-2. So that shows that, okay, now we are moving down, meaning that if we have 4 carbons there, it will be C4H6. You can see C4H6. So we have moved from C4H10 for alkenes with the maximum number of hydrogens. When we go to alkynes, we remove 2 hydrogens, we got C4H8. When we go to alkynes, we remove another 2, we got C4H6. I hope you have understood how to move from general formula of alkanes to alkenes and to alkynes. And we're saying alkanes on their own, they are referred to as homologous series. And alkenes are homologous series, alkynes homologous series. As I indicated, that we have 9 homologous series in technical science. Now, how do you define the homologous series? We're saying this is a series of organic compounds that can be described by the same general formula. So it's important for you to know the importance of the general formula, because when you define your homologous series, you will now say all the homologous series are defined by or described by the same general formula. So if you belong to the same homologous series, your general formula must be the same. And each member will differ from the next by the CH2 group. You can see when we move from propane here, the difference there is a CH2 group. It shows that they belong to the same homologous series because each member differs from the next by CH2 group. I hope that helps you to have these basics, because they will help you now as we go to do the questions, so that you know where the questions are coming from. And we're saying these hydrocarbons, they can be unbranched or branched. So it can be straight chain or it can have branches. So you can see we are having a unbranched alkane, unbranched alkene, and unbranched alkyne. So all of them are unbranched. And then we are saying now these other ones, they are branched now. They have a branch. You can see there we have a branch. So we have a branch, we have a branch, we have a branch. So all the hydrocarbons can be alkanes, alkenes, and alkynes. We're saying they can have a branch. So they can have a branch. How do you know that it is a branch? I usually would say just draw a line without lifting a pen. If you are able to draw and you cover the highest number of carbons, that will be your parent chain, and the other carbons that you are having will be part of the branch. For example, if I draw a longest line there, I will say this is my longest carbon chain. So now it shows that the other one is a branch. Sometimes we refer to it as a substituent, because remember where that CH2, CH3 is, we have removed a hydrogen. Hence, we can say we have substituted that hydrogen with that ethyl group. Hence, we interchange it to refer to it as a branch or substituent, and that, so that you are not confused when it comes to that. Now, the other thing that we emphasized on this slide was that these branches can be found in alkanes, alkenes, and alkynes. In real sense, almost all these homologous series, you will find that they do have these branches that they can have. Now, this is the most important slide when it comes to naming of organic molecules. This must be your friend. It must be close to you. To say in technical science grade 12, we name only six carbons. So we don't go beyond longest chain. Our longest chain will never have more than 6 carbons. So you have to know at all times that we must have 6 carbon in our longest carbon chain. There must be 6 carbon. Hence, we are indicating when you find a structure with 1 carbon, this which I'm talking about, it applies to alkanes, alkenes, alkynes, and haloalkanes. I will tell you later why it applies only to those. Now, if you have one carbon, then we're going to say it's meth. When it's 2 carbons, it's 3 carbons prop, 4 carbons but, 5 carbons pent, and 6 carbon hex. So please always remember that the number of carbons will determine the name that we are going to give to the structure. Now, this is what we will write. We'll start the name with. Then I wrote it there as a prefix. You must not confuse this prefix with the substituent or the branch. Your bromo, your chloro, your methyl, and your ethyl, which we will talk about just now. So you have to know that this is your stem. You're looking at how many carbons do we have in the longest carbon chain. So if it's 1, you will say meth. 2, you will say eth. 3 prop, 4 but, and 5 pent, as well as 6 hex. So please do that so that you don't have a problem of naming. Remember, even as we mark, we will always acknowledge that, oh, you are aware that it's 6 carbon. You wrote hex, then we are able to give you a mark for indicating how many carbons are there in the structure. So everything here that is on the slide is very much important. Look at this. If it's an alkane that you are naming, so it means you will start with meth. The suffix is name ending. How will the name end? The name will end with the ane if it is an alkane. So you have to understand that. To say the name end depends on the homologous series. To say which homologous series is this one. So you can see that if it's an alkane, it will be methane, ethane, propane, butane, pentane, and hexane. So you know you do up to 6. So it's very much important that you understand that. And when you are doing the naming of your structures, you are always going to start there to say what is the functional group, because when you get the functional group, it will tell you which suffix do we have. Then when you know, for example, when you look at the structure, it's made up of carbons and hydrogens only, you know it's a hydrocarbon. And when they are only single covalent bonds, you will know that it's an alkane. If it's an alkane, you know that the name will end with the name. The second step will be to look at how many carbons do we have. If we have 3 carbons, you will say here the parent chain or the longest carbon chain, you will say it's 3 carbons, then you will say it's prop. So when you name, you simply start from here, you will say propane. But if there is a branch, let's say in carbon number 2 there is a branch, you will now go to be your prefix. So when you are naming, you will put your substituent first. Let's say in carbon number 2, you have a bromo, so you will start from there, you say 2-bromo propane. So that becomes your name. I just want you to get that because if you understand naming, if you understand where this is coming from, then you will be able to understand the entire topic. But if you don't know the names of the structures, you're going to have a challenge, because we will ask you to draw structural formulas for some of them, molecular formulas, as well as the general formulas, as well as naming the molecules that you will be given. Now, again, I indicated that this method of using meth, eth, prop, but, pent, and hex, we use it for hydrocarbons and haloalkanes. Remember, haloalkanes, we're treating them as substituent on the alkanes, hence we take them together with the alkanes. Because if you are given a haloalkane, for example, if you are given a structure like bromo, like that, let me just give you a simple structure, bromomethane, for example, you will see that bromo is a substituent, but you are saying the name is methane. You see, saying methane, they're just putting bromo at the beginning, so it's bromomethane. So you are still treating it as an alkane that has a substituent that is a halogen, hence the H there for haloalkanes. So I understand. I want you to look at haloalkanes differently and classify them as you name. Look at them as alkanes that have a halogen in them, so that you are not confused to start to treat a halogen like a functional group that you have. So I hope that clarifies that and you won't have a problem, because the name there, the parent name, will be A for alkanes, but the bromo, a substituent, you're going to acknowledge its presence, and you always indicate the position where your bromo is. Now, when it comes to aldehydes, ketones, esters, alcohols, and carboxylic acid, those remaining groups, because we are doing 9, which is, we talked about the first 4, which is alkanes, alkenes, and alkynes, and haloalkanes. Now, when you talk about aldehyde, ketones, esters, alcohols, and carboxylic acid, you are able now as well to look at them and say, for these ones, the prefix will be methane. So you now write the whole name like methane, but without E. You remove the E, only the E there. So you'll write them like they are alkanes without E. Then you are going to use the homologous series will tell you how the name will end, which is your suffix. For example, if you are dealing with aldehyde, you will say methanal. Because we have learners who make a mistake during exam and they write methyl. So that will be wrong. It cannot be methyl, it must be methanal. Hence we are saying write the whole methane without E. Just remove the E there. Then the suffix, you take it from the homologous series. To say it's an aldehyde, it will be methanal, ethanal, propanal, butanal, pentanal, hexanal. Are we together? I hope you get that correct. When it comes to ketone, they only start from 3 carbons. Remember, for ketone, we're saying the C double bond O must be surrounded by 2 carbons. Hence, you will start with propanone, which is your first ketone that you have. When it comes to alcohol, you just put the "ol" at the end. So you still write methane, ethane, propan, butan, pentan, and hexane, but now it will be methanol, ethanol, propanol, butanol, pentanol, and hexanol. So you are able to do that. The same now applies when you deal with the carboxylic acids. For carboxylic acid, you are adding the suffix, which is oic acid. So it will be methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid, and hexanoic acid. So I hope you got that. And we are saying our substituent here is our bromo and our chloro. Our side chain or branch is our methyl and ethyl. So we only do those 4. So just know that if the structure has a branch or a side chain, you will acknowledge its present and you will indicate in which carbon do we find methyl or ethyl, in which carbon do we find the bromo or chloro. So this substituent, side chain or branch, always we number them. You always indicate the number where we find them. And in most of our structures, you find that we have 2, maybe you have two bromos that are substituted in one structure. So if there are 2, you will say dibromo. If there are 3, you will say tribromo, 4 tetrabromo. Then the name of the alkane. I hope you get that and it will help you, as now we're going to do activities. We're going to do naming of organic molecules, looking at question 2, which is one of the questions that you are writing, but sometimes you have a challenge about that. Now, when you get a table like that, the emphasis is that look at first the functional group. From which functional group, as I've done this to remind you, which is your FHMC, to say the F there is the functional group, to say from, because for you to know the homologous series which the structure or the organic molecule belong, you must first know its functional group. So I'm emphasizing that the first thing when you look at the structure, look at the functional group. In this case, our functional group is a carbon-carbon double bonds, which you know is for alkenes. It's for alkenes. So the functional group is carbon-carbon double bond. Homologous series is alkenes. So you're able to check that this belongs to alkenes. And then you can be able to write the general formula for alkenes, because you know the general formula for alkenes. We talked about it. You said CnH2n. You can be able to get the molecular formula. Remember how to get the molecular formula. You're simply saying how many carbons do we have. So you'll say C2. We have 2 carbons. How many hydrogens? H4. That is the molecular formula. So you're able to move from general formula to molecular formula as I've shown when we started with our lesson. Now, structural formula, you show all the bonds. Hence, you see what you are given here. It's a structural formula. So the only thing that we don't have, you can even condense it and say CH2, CH2. So we won't be confused. When you see CH2, CH2, you know that there must be a double bond between those two carbons. So these are our formulas that we do. You condensed, and then you must know the name. And we said when you have 2 carbons, remember, you look at the structure, you say it's a hydrocarbon. So remember, we said for alkanes and alkynes and hydrocarbons, we use bromide, eth, and then prop up to hex, because we do 6 carbons. So in this case, we have 2 carbons, which means it's an eth. But what is the family? We start with the suffix. What is the suffix? It's alkene. It's an in. So you'll say this will end with in. So suffix. What is the parent or the longest carbon chain? Is 2 carbons. You know when it's 2 carbons, it's eth. So you will say, okay, parent. Here we're having 2 carbons, so it's eth. So when you name this, you will say ethene. Then you are able to name the structure and you are able to collect your marks. The same if you were to go to number B, to look at B there, to say what is the functional group. You start there. Always look at for you to be able to identify, you have to know the functional group. The functional group is that when you remove from a structure, you remain with hydrocarbon. So you can see, and let me put it this way: if you remove the functional group, you'll remain with an alkane of some sort. So, for example, if we were to remove this, we can remain with carbons and hydrogen and the single bonds and all that. So you know that, okay, this is our functional group. It is for aldehydes. We call it 4-mile group. Remember, for aldehydes, I've emphasized that for aldehydes, we call it a 4-mile group. And we said these aldehydes, the homologous series is called propanal. So the homologous series will be propanal. So you are able to see that, okay, it's 3 carbons. How do you go about it? The same method that you are doing. You will say, okay, what is the suffix? The suffix is from the functional group, which is your homologous series, which is an aldehyde, so it must be an al. How many carbons? 3 carbons. And you know, you won't say prop, you will say propane. Remember I said you write the whole name for this remaining other 5 homologous series. You write the whole name of an alkane without E. Then you'll say propanal. So the name of that will be propanal. I hope this helps you as you revise and you start to see that this is simple and you can get many marks. Now, you will be given structures like number C, which is now a molecular formula, because we don't want you to understand only one type of formula. We want you to understand all the formulas that we use. For in case this one is a C3H4, if you are given a molecular formula, first draw the structure, because it can really be confusing to know where it belongs. So when you look, you have 3 carbons, so you must just draw the 3 carbons there to indicate that, oh, we're given 3 carbons, and then the 3 carbons, and then how many hydrogens? 4. So the hydrogens there is 4, so it's 1, 2, 3, 4. So we must be having a triple bond there, because each carbon must have 4 bonds around it. So if this carbon has 4 and this one has 1, 2, then there must be a double bond so that it has 4. So each carbon, if you check, always when you do structural formula, check the number of bonds around each carbons. They will definitely show you that you have drawn a correct structure. So you are able to see that, okay, this must be triple bond, it must be an alkyne. So the homologous series is an alkyne, the functional group is a carbon-carbon triple bonds. So you're able to look at that and be able to enjoy your paper. Now in number D, you are given pentane there. Now that you are given pentane, you know pent is 5. It's 5 carbons and it's an A. So all you are doing is to draw 5 carbons. After you have drawn the 5 carbons, you ensure that around each carbon there are 4 bonds around each of them. Then you draw each of them, you draw each of them, you draw each of them, you draw each of them. Then you get that. Don't forget, if you write propane like this, it's a nice wrong that you got yourself. Propane has hydrogens, so you must indicate all the hydrogens that are there around the carbons and all that, and then we will get all your marks. So you draw propane, you are able to draw the structure. So always when we've given you a name, draw it. When we've given you a molecular formula, draw it, because it becomes much clearer when you have drawn the structure. You can see for number F, we are given ethanoic acid. So ethanoic acid, you will know that the functional group there is the carboxyl group, not carboxylic group, but carboxyl group. So I'm emphasizing the importance of you understanding the functional group. And if you know the functional group, it becomes easier to know the homologous series, which in this case, it will be carboxylic acid. So the homologous series will be carboxylic acid. So the group is not carboxylic group, it's carboxyl group. You can see all our group, they end with a YL. We have a hydroxyl group, we have a formyl group, we have a carbonyl group, we have a carboxyl group now. So you see that these groups, they go like that, which is our functional groups. I hope you won't forget that the carboxylic acid is a carboxyl group. And don't forget the general formula for carboxylic acids is CnH2nO2. That is the general formula. The general formula for carboxylic acid. But in this case, we are given ethanoic acid. You know, ethan means 2 carbons. So you will know that ethan is 2 carbons. So you can draw the 2 carbons. And for the carboxylic acid, you have a COO there, which is a C double bond O and an OH. Then you know that you are able to draw your structure for carboxylic acid. And always ensure the number of bonds around each carbon are 4. I hope you have understood what we have been doing, this activity. And you can go through each question paper that we have from 2018 to this day, and you revise all of them and ensure that you remember and you are able to be ready for the coming exams. Now, these are the questions that we asked, but you will have realized that when I was taking you through the strategy to say how do you go about resolving these problems using only the table before you even look at the questions. And then immediately when you go to questions, you will see that majority of questions are what already we talked about. You can look here at question 2.1. They're saying define the term organic molecules. And we've indicated when we started this lesson that organic molecules are the molecules that contain carbon atoms. They must have carbon atoms. There are exceptions like carbon dioxide. Carbon dioxide is not an organic molecule, but it contains carbon. It doesn't mean that because you have a carbon, now you qualify to be an organic molecule. Most of our organic molecules, they'll have carbons, they'll have hydrogens and all that. But now when it comes to the definition, we're saying organic molecules are molecules containing carbon atoms. Like all these molecules that we have here, they are organic molecules, and when you look at them, they have carbon atoms. I've shown you an exception of carbon dioxide. Now we are saying write down the name of the homologous series of the following. So now remember that activity we're doing, you're checking all of them, what is the homologous series. So it becomes easier now to come and look at number A, as we've been doing. We said it's an alkene because of the double bond. So you're able to say A is an alkene. You go to 2.2.2, you look at C, you're able to say, it's not easy for you to determine the homologous series if you don't draw the structural formula first. So the emphasis will be first draw the structural formula and see all the bonds. We did that and we were able to draw the structure. You saw we had a double bond there, we had a hydrogen, we had CH3 there, and then it was like that. Then you are able to see that this is an alkyne. So you said this is an alkene, and then number C, you said is an alkyne. So you are able to see all that and with no problem. Now let's look at 2.3. 2.3 is saying draw the structural formula of the compounds represented by the letter. Now you have to draw, which is what we were doing. We have drawn D and F. If I go to the previous slide, you will see that we said pent is 5. We said you are drawing the 5 carbon. You are writing down the 5 carbons bonded to each other and ensure that you put the hydrogens, all the hydrogens around it, which will be your C5H12. Ethanoic acid, we said ethane is 2 carbons. We're able to draw the structure and say that is the structure of ethanoic acid. So you see, you are getting your marks for pentane. We said it's 5 carbons. You're just throwing 5 carbons like that. You ensure that there are hydrogens around, and each carbon must be surrounded by 4 bonds around it. You ensure no mistake is made, because we literally count them when we're doing marking. So if you make mistakes of putting an extra or one less hydrogens, you won't get the structure correct. So imagine you will have got the 2 marks and the 2 marks for the F there, and you collected the marks. Write down the IUPAC name of compound E. So as well, you are able to go to compound E. Remember what we said. We said the first thing that you must do is the suffix that we get from the functional group. So you will check that structure and say, what is the suffix? What is the functional group here? Is there any other group? Nothing. When there is nothing, you know we have alkanes. So alkanes, they end with A. But now, how many carbons do we have in the longest carbon chain? Because you want the parent. For you to get the parent, you will say, how many carbons do we have in the longest carbon chain? Then you're able to say, we have 1, 2, 3, and 4. So you know that we have 4 carbons in the parent chain. And in carbon number 2, you have a methyl. In carbon number 3, you have a methyl. Remember why we refer to it as a methyl. Remember a CH4, we call it methane. But this one, because it's not a CH4, it's a CH3, we don't say methane, we call it methyl. So as a substituent, we refer to it as methyl. So you will see that we have a methyl in carbon number 2, we have a methyl in carbon number 3. The parent we said is 4, and 4 is put. So you'll see parent is put because of 4 carbons. Then what is the name ending? I mean, the prefix, the name will always start. Remember, we said names would always start with a branch or a substituent. Bromo, chloro, methyl, or ethyl. As long as there is a branch and there is a substituent, you ensure that the name, when you write, you start with that. What is our substituent? Is in carbon number 2, we have a methyl. In carbon number 3, we have a methyl. So because they are 2, we'll refer to them as 2,3 dimethyl. So you'll say 2,3 dimethyl, and then butane. Then you write butane. Don't forget, between the 2 numbers, you put a comma. Between a number and an alphabet, a D and 3 there, you put a hyphen. Please, we always penalize and take 1 mark for not writing the hyphen or the comma and all that. So don't be more excited as you are getting this correct. Ensure that you are able to do and get each and every mark, because each and every mark is important. Remember, we have 47 marks that comes from here, which is your 62% of your paper. So you ensure that you do well in organic chemistry, then you will know that paper 2 will be the simplest topic for you. So you are able to get your 2 marks there for writing 2,3 dimethyl butane. And then in 2.5, they said for compound B, write down the name of the functional group for compound B. I think we've done it that side, to say when it's a C double bond O and a hydrogen bonded to a hydrogen, that must be a 4-mile group. You can call it 4-mile group or 4-mile group, is fine. Fortunately, technical science is not an oral language. We don't do oral here. You write your answer. So we'll mark 4-mile group, the one that you have written. Thank you very much. Now, when it comes to the molecular formula of compound B, remember how we got molecular formula? We're simply saying how many carbons. So we have 1, 2, 3. So you will say it's a C3 because we have 3 carbons. And then you count your hydrogens. It's 1, 2, 3, 4, 5, 6. So you'll say it's a C3H6 and then O. So it's a C3H6O. Then that gives you your molecular formula, you get your 1 mark. Just imagine you will have collected your 12 marks, you will be celebrating now. Now, without any wasting of time, I think you have got to understand when it comes to naming. I will go now to isomers. Let's look at isomers. Remember, we do structural isomers. We define structural isomers as organic molecule with the same molecular formula but different structural formula. So please know this, because most of the time we'll ask you to define chain isomer, positional isomer, and functional isomer. But there are times when we just say define isomers or define an isomer. So you must know that they have the same molecular formula but different structural formula. We have 3 types of structural isomers, which in this case is your chain isomers, your positional isomers, and your functional isomers. Now we're saying the chain isomers, they have the same molecular formula but different type of chain. As given here as an example, we have butane, which have a longer carbon chain, a unbranched chain, and you have 2-methyl propane, which is branched. So you are able to see what these are different type of chain. But for it to qualify to be a chain isomer, they must have the same molecular formula. So you have a responsibility to count how many atoms do we have here in each of them. So let's look, for example, at butane is 4 carbons, so it's a C4 and H10. So butane is C4, H10. And then let's look at 2-methyl propane is still having 4 carbons, so it's a C4, 3, 6, 7, 8, 9, 10. So it's a C4, H10 as well. So they have the same molecular formula, but are the chains the same? No. One is branched, one is unbranched. So this is different type of chain. So they qualify. Butane and 2-methyl propane are referred to as chain isomers. I hope you got that. You cannot have a chain isomer where the other one has 5 carbons and the other structure has 4 carbons. No, the amount of carbons as indicated in the molecular formula must be the same. So they must have same number of atoms and in equal proportion to each other. Now, let's go to positional isomers. Now, obviously, the nice thing is that what remains the same is the same molecular formula. So we're given the example here, 1 chloropropane and 2 chloropropane. So you will understand that these are positional isomer because our substituent chloro is in carbon number 1 in the first structure and chloro is in carbon number 2 in the second structure. So you are able to see that, oh, we have moved the chloro from carbon number 1 to carbon number 2. So those are positional isomers. Hence we are saying they have the same molecular formula but different position of the substituent, of the side chain, or of the functional group. So you can write that. And then you are able to say same molecular formula but different position of the substituent, of the side chain, or the functional group. That is how your exam guideline defines positional isomers. Then we have but 1 in and but 2 in. If we move the double bond to second carbon, it becomes but 2 in, but it will have the same number, same molecular formula, but different position of the functional group. Because if the functional group is in carbon number 1, it will be but 1 in, but if the functional group is in carbon number 2, then it will be but 2 in. Then we are able to move forward. Now, functional isomers, here we're usually saying cake so that we don't forget that which we use to say carboxylic acid, they go with esters. So the functional isomers of carboxylic acid are esters. And for you to remember the general formula for carboxylic acid is CnH2nO2, which is the same as the one for esters, CnH2nO2 as well. So you're able to see that esters and carboxylic acid, they have the same general formula. And when it comes to aldehydes and ketones, you will be able to see that your aldehydes, they have the general formula CnH2nO, which is the same for ketones. And those two we say are positional isomers. I mean, they are functional isomers. So they have the same molecular formula, same general formula, but different functional groups. They don't belong to the same, they don't have the same functional group. And if the functional group is not the same, even the homologous series won't be the same. Remember, the chain isomers and the positional isomers, they all belong to the same homologous series. So it means when you look, all of them will be alkanes, all of them will be haloalkanes for positional isomers. But when it comes to functional isomers, they must be different functional group. But the molecular formula is the same. What is different will be the functional group. I hope you've understood that. And as you get questions that are based on that in your exams, you'll be able to respond and get them correct. Now, if we look at what we refer to as physical properties. Our physical properties for technical sciences, we are focusing on the four physical properties that we do, which in this case is our melting point, boiling point, vapor pressure, and viscosity. So we must know the relationship of these physical properties for alkanes, alkenes, alkynes, alkali, for all the 9 homologous series. And then we must be able to look at as well the strength of the intermolecular forces. Now, remember, in tech science, our main focus here in grade 12, we focus on the London force, the dipole-dipole, and the hydrogen bond. So that becomes the focus of our physical properties, to say these are the intermolecular forces that we're having. Remember, for you to melt ice, you must first overcome the intermolecular force. Remember, ice is having hydrogen bonds. So the structure, hence you see, is very compact because the intermolecular forces are very strong in ice. Hence you need energy. You can put it in the sun there because you are increasing the energy. When you increase the energy, you are overcoming the intermolecular force. Remember, you are not breaking down the bonds, because if you break down the bonds of water, you won't have water. But when you are overcoming, you are saying, I still have water, but I'm changing it from solid to liquid. Again, you increase the force, the energy again. You will still have water, but in a gaseous form. So you are changing the phase from solid to liquid to gaseous form. Hence, we don't break, but we overcome the intermolecular force. Language is very much important to know that we're going to overcome the intermolecular force in order for us to change this from one phase to another as well. Now, that's what we're going to do. And our focus here is we're going to look at the intermolecular force, our functional group, our chain length, our molecular mass, and our branch. And I always refer to this as that which we are changing during this. Look at question 3, look at physical properties as an experiment, where these are your independent variables that you are going to change during that experiment. It's either will change the branch, will have branches, increase the number of branches, will increase the molecular mass, will increase the chain length, or will have different functional group, which will mean that we will have different intermolecular forces. So it's very much important that you know that what we change is this which I've indicated there as if chain mob, so that you are able to remember. Remember, that which you change to the experiment is your independent variable. And that which you measure, in this case, we said we measure 4 things. We refer to that as dependent variables. So our dependent variable is our melting point, boiling point, vapor pressure, and viscosity. So this will be our physical properties that we are dealing with, so that we are able to move forward with no problem.
The road to success is to commit to yourself. In order for you to become who you want to become as a student, you need to commit to reading your books, to studying, to bettering yourself. I know it's not going to be easy. Actually, no one said it's going to be easy. But if you put in the work, the results will show in your life. Tap into your power. Sometimes you will feel like putting away your books, and not reading as much as you're supposed to be. But I want you to commit, because through commitment, there is infinite power.
Yes, so we are still busy with our physical properties, and I'm hoping that you are understanding that we are going to focus on intermolecular forces, which we said the three intermolecular forces. It's our London force, it's our dipole, it's our hydrogen bond. So these are the forces that we find that are holding these structures or these organic molecules together. So it's very much important to know that for us to have the melting point, boiling point, vapor pressure, and viscosity, it depends on the strength. So we'll always be looking at the strength of the intermolecular force, to say what is the strength, is it stronger, is it weak, how much energy will we need. So we have this ICE principle that we use when it comes to this question, to say we're going to look at the independent variable, which can be your intermolecular forces, to say what is the difference in terms of the intermolecular force, and then we compare the strength of the intermolecular force and then the amount of energy that is needed. So we'll always look at the structure first to say, oh, these structures, what is different amongst them? Remember, that which we are changing is our independent variable, and that which is different, then it will tell us to say, are we going to have higher boiling point or higher melting point or viscosity? I hope you got that. As we move now to deal with the questions, here we're dealing with physical change. As I indicated, that if you have water, you still have water, but you can have it in a solid form, which means the intermolecular forces are very strong. But when you move to liquid form, you have overcome the intermolecular forces. So what is that's why we're not breaking it, because we want the molecule, the organic molecule, to remain there, but in a different state. Now, we are saying these are examinable physical properties, which is your melting point, boiling point, vapor pressure, and viscosity, as I indicated. And we are saying that melting point, please collect these marks for definitions. If you look in technical science, every question we have definitions. All the questions, when they start, we have definitions. So collect these marks of definitions so that we don't have the problem of you not getting these marks. So we've defined for you the melting point as a temperature. We still emphasize it's not a point, it's a temperature at which the solid phase and the liquid phase are at equilibrium. The solid phase and the liquid phase are at equilibrium. Boiling point, as well, we're saying is a temperature. Please don't make a mistake of saying it's a point. Immediately saying it's a point, we're taking a mark away from you. So ensure that you are saying it's a temperature at which the vapor pressure is equal to the atmospheric pressure. That is for boiling point. When it comes to vapor pressure, we're saying it's a pressure exerted by vapor at equilibrium with its liquid, in a closed system. So when you talk about vapor pressure, it must be in a closed system. Now, viscosity, we said, is that property of a fluid to oppose or to resist the relative motion between two adjacent layers. So that is your viscosity, that property of the fluid to oppose or to resist relative motion between two adjacent layers. You have seen we have done an equation there that indicated that if we have a high viscosity, then our fluid will flow slow, and because it has high, the strength of intermolecular force is higher. So you have to understand that and be able to move with that with no problem. Now, these intermolecular forces, I know that you have done as you revise, so I'll try to go through them so that we look at the question. So we are saying we have alkanes, we have alkenes, we have alkynes. All these hydrocarbons, they have what we refer to as London forces. So these ones, they only have London forces. But when you look at Hake, which is your haloalkanes, aldehydes, ketones, and esters, they have London forces and dipole-dipole. However, when you refer to them, we'll refer to dipole-dipole because if you acknowledge the existence of dipole-dipole, you are acknowledging the existence of a London force. Now, when it comes to alcohols and carboxylic acid, you must look at them very well. They have the London force, dipole-dipole, as well as hydrogen bonds. But now we are saying here we will focus on the hydrogen bonds, we'll focus on the dipole-dipole for these four, and for hydrocarbons is London forces. Now you can see alcohols, because they have only one O there, they can form, they have one site, we say they have one site of hydrogen bond. But carboxylic acid, they have two sites. Because of the presence of two oxygens there, it has two sides, oxygens and hydrogens. It has two sides of hydrogen bonds. Hence, you will find that carboxylic acid are the strongest intermolecular forces because they are able to form those two hydrogen bonds as compared to the alcohols that will form one hydrogen bond. I hope you understand that and you are able to move with that with no challenge. Now we are saying we're going to look at the strength. Remember, the London forces are the weakest intermolecular forces, but when it comes to dipole-dipole, they will be stronger than London force, but they will be weaker than hydrogen bond. Please, I emphasize, don't write hydrogen bond as H bond, just write hydrogen bond in full. So the strongest intermolecular force are the hydrogen bonds. Now after that, we look at the strength. After the strength, we look at the amount of energy that will be required to overcome the intermolecular force. This statement, you must write it in full to say when you talk about energy, we are talking about the energy required to overcome the intermolecular force. Whether it's more energy is required or less energy is required. So you are able to move to say the least amount of energy is required to overcome the intermolecular force, or more energy is required. More energy is required when it comes to Hake, which is your haloalkanes, aldehydes, ketones, and esters that have dipole-dipole. You will need more energy than London forces, but you will need less energy when you compare it to hydrogen bond. I hope you get that. And lastly, we're saying the most amount of energy is required to overcome hydrogen bond. So hydrogen bond, they require more energy. And even when it comes to alcohols, you will need more energy, but when it comes to carboxylic acid, you need even much more energy compared to alcohols, because we are saying carboxylic acids have two sides of hydrogen bonds. So have that distinction so that you don't have a problem of not knowing what's happening. Now let's look at the question so that we move as we go towards the end of our lesson. We're saying in question 3, the table below indicates the vapor pressures of 3 organic molecules. You see, be very careful when you're dealing with vapor pressure, because they can easily confuse you. Remember, when the strength of intermolecular force increases, the vapor pressure decreases. Hence, we like to assess many questions based on vapor pressure because of that. Remember, when it comes to melting point, boiling point, and viscosity, we're saying as the strength of intermolecular force increases, even them they increase. So it becomes easier for you to deal with those. But when you are dealing with vapor pressure, when the strength, so when the intermolecular forces are stronger, the vapor pressure will be lower. So you get to have that distinction when you are dealing with vapor pressure. Now we're saying the first thing, as we indicated, definitions, please, and we are using exam guideline to do our definitions. So please spend time doing your definitions. So we're saying define the term vapor pressure. Remember what we said? We said it's a pressure exerted by vapor. So take it from the name there. It's pressure exerted by vapor at equilibrium. Pressure exerted by vapor at equilibrium. We'll write equilibrium in full. At equilibrium with its liquid. At equilibrium with its liquid in a closed system. In a closed system. So that's what we are saying is a pressure exerted by vapor at equilibrium with its liquid in a closed system. Now we are saying which compound, A or B? So the question is asking is based on A or B, has the higher boiling point. So you will look at pentane, you will look at 2-methyl butane. So remember, as the number of branches increase, the strength of intermolecular force decrease. And as the strength of intermolecular force decrease, boiling point decrease. So you have to take it from there to say if an organic molecule has a lowest vapor pressure, it means it has highest boiling point, melting point, and viscosity. In this case, they're asking about boiling point. So your point of departure is to say if we have lowest vapor pressure, it means we have highest boiling point. So the question said, which one is the higher boiling point? So you will say pentane. You get your 1 mark, or you can just say A, because the question we said A or B. So your answer must say A. Explain the answer to question 3.2 by referring to the structure. So the first thing, you are going to look at the structure, which is our independent variable, to say what is different in these structures. So you can see pentane, no branch, 1 branch, and then we have 2 branches there. So you can see that we are increasing the number of branches. So you can see that, okay, that the structure is that as we increase the number of branches, we're increasing the number of branches. What happens? Remember, you must answer in bullet form here. We don't want you to write a letter because we mark each bullet independent of the other, so that if you make mistakes, we're able to acknowledge the other points that you are making them correctly. Now, you will look at the strength of the intermolecular forces to say, okay, which one is stronger between A and B? Remember, our question is on A and B. So we are saying A, no branch. B is branched. That is the first thing you are saying. The second thing that you are going to look at, that is the structure. You are comparing the structure first. Number 2, you are going to look at the strength of the intermolecular. We are saying which one has the higher strength of intermolecular force. So all of them, they have London force, but as the branched one will have less strength of intermolecular force. So you are saying the intermolecular force in A is stronger. So A has a stronger intermolecular forces than B. A has a stronger intermolecular forces than B. That is your second point, because the first point was on the independent variable. What is changing? What is different between them? The second bullet, you are saying which one has the strongest intermolecular force, which in this case you are saying is A more than B. Now, the third one is energy. So if it's stronger for A, then more energy will be required. More energy will be required to overcome intermolecular forces in A, in the stronger one. So you need more energy to overcome that. And then you are able to get your 3 marks. So I hope that assists you and helps you in you getting this question correct. Now, we are saying what type of structural isomers are compounds A, B, and C? Oh, isomers. How many types of structural isomers we talked about? We talked about 3 types of structural isomers, which in this case we said is a chain isomer, is a positional isomer, and a functional isomer. Remember, in all of them, we said they all have the same molecular formula. So these are the statement is saying they are structural isomers, which means the molecular formula is the same for all of them. But what is different between them? You can see that the number of branches is what is different. So we're talking here about the chain, the different type of chain. While others are not branched, the other is one, it has 1 branch, the other one has 2 branches. So you can see they have the same molecular formula but different chain types of chains. Same molecular formula, but different types of chains. So the type of chains are different. So you know these are chain isomers. Give a reason for your answer. So you can see that already you are saying, okay, they are chain isomers, A, B, and C, the chain. Give a reason. So you are saying they have the same. Most of the time in paper 2, please get this one. When we want a reason, you will find that the definition will be a better explanation. Like in this case, we're saying, why do you say A, B, and C are chain isomers? So you just define it to say they have the same molecular formula, but different type of chain. And then you got your 2 marks, you have your 9 marks. This was the paper that was written in June. I hope this helps you as you prepare now for your final paper. Let's go to the last question, which is question 4. Which are the reactions of organic molecules? Now, here in technical science, we do addition reactions. We do addition reaction. That's what we do. We do addition reaction. We do substitution reaction. We do substitution reaction. We do oxidation or combustion. So you can call it oxidation or combustion. And we do esterification. But in terms of esterification, you just have to identify the alcohols that are used and to be able to name the ester and all that. So that's what we do. So we look at those 4 types of reactions as well. Here, I don't have to forget that we do polymers as well, which is the last thing that we do in terms of organic molecules. So this is what we must look at. And in this case, for addition types of reaction, now this has never been easier, because when we say USA, we're not talking about a country. We are saying when you see unsaturated hydrocarbons becoming saturated, remember unsaturated as a double bond or a triple bond. In this case, we only do double bond. So what we are simply saying is that when you see unsaturated becoming saturated, you know it's addition. Now, I always say this to learners to say, when you see a double bond, you know the type, every arrow that comes from here. If I'm to do any arrow here, you must know that all of them, they are addition reaction, because our unsaturated and for our scope for grade 12, we're saying we do addition reactions when we have unsaturated hydrocarbons. So you're able to look at that and say, okay, now it only depends what type of addition. It depends on what we are adding. In this case, we do 4 types of addition. So there are 4 addition reactions that we do. There are 4 addition reactions that we do. The first one being hydrogenation, when we are adding hydrogens. And when we say write down structural formula, you must be able to show the bond between the H and H. Remember, structural formula says show all the bonds. So it's very much important. Then we add the H and H on the double bond. Then we call that hydrogenation. And we have reaction conditions, or the catalyst that we use is platinum, palladium, or nickel. So you can see that where we add on the double bond, so where you can see that there we can have a bond, an H there, we can have another H there. So when you add on the double bond must disappear, because remember how we formed the double bond, we removed the hydrogens. So if you are taking the hydrogens back, the double bond must disappear. So you are able to add there, and then we will have a structure without a double bond, and the hydrogens will be there and there. And then we call that reaction addition reaction. What type of addition? We call it hydrogenation. What are the reaction conditions of the catalyst that we use? It's platinum, palladium, or nickel. You can just know them as PT, PD, or nickel. So the other reaction that we have is hydration. Hydration, we are adding water. Water, the structure of water being like that, which means on this now double bond, we're going to add OH in 1 carbon and hydrogen in 1 carbon. Now, it's very much important for you to understand that the OH for the major product, the OH will go to the poorest carbon. The OH will go to the poorest carbon. The hydrogen will go where there are many hydrogens. So when you have water, you must know that for us to get a major product, the hydrogen must go where there are many hydrogens, and the OH will go where there are less hydrogens. In order, I try sometimes to simplify this to say, if you are having OH and H looking for a seat here, let's say this is a taxi, and you find that we are having a seat that has only one hydrogen, another seat with 2 hydrogens. So you are able to see that indeed OH, because it's bigger, we have 2, we have oxygen and hydrogen, will go where there are lesser number of hydrogens in that seat. So in this seat we have 2 already, hence the hydrogen will come here, we'll have 3 of them, but the OH will go where there are less number of occupants there. I hope it helps you as you remind you where the OH will go and where the hydrogen will go. And the reaction, we refer to it as hydration because we are adding water. And remember, where there is water, sulfuric acid want to follow. So sulfuric acid is a nice dehydrating agent. So our reaction condition or our catalyst is sulfuric acid. There must be sulfuric acid present when you are doing addition of water. Now, we have addition of a halogen, the group 17 elements. As indicated, we only focus on bromination and chlorination. So we only use bromine, Br2, and Cl2 when we do the addition. In fact, for the rest of our organic chemistry, for group 17, we focus on the bromo and the chloro. Now, for this halogenation, obviously, one bromine will come to one carbon and another bromine to another carbon. So it becomes easier when you are doing halogenation. The good thing about halogenation is spontaneous. You don't have to use any catalyst. Immediately when you add Cl2 or Br2 there, it will just go and add on the double bond. It doesn't need any catalyst. That is the addition reaction. The last type of addition reaction that we do, the 4th one, is our hydrohalogenation. For hydrohalogenation, we are saying no water must be present. That is the reaction condition. So if there is water, you are going to have problems where water instead of ACl or HBr now is added. So we are saying no water must be present when you are doing addition of your ACl or of your HBr. So don't forget the reaction condition. Remember, for your simplicity, we're saying USA, we stand for unsaturated becoming saturated. The reaction is called addition. So we're saying when you see a double bond, you are seeing addition type of reaction. And the explanation there, we're saying when you have a double bond becoming single bonds, it means you have added. And we said every arrow that comes from there, as far as this question is concerned, that will be addition reaction, depending on what we are adding. So we will always look at what we have added, then it will tell you whether it's hydrogenation, hydration, halogenation, or hydrohalogenation. Now, we have substitution as our other type of reaction. Remember, the nice thing about substitution, we're saying is saturated substitution. So when you see a saturated hydrocarbon forming another, saturated means no double bond. We said saturated means that single covalent bond between carbon atoms. And if you see here, it's only single covalent bonds. There's no double bonds. Then that is saturated. So all the time when you have saturated forming saturated, the reaction, we call it substitution. And the first one that we do is halogenation, where we use Br2 or Cl2. But now the good thing about substitution, unlike addition, remember in addition we add all the Brs there, but in substitution we are going to substitute one hydrogen by one bromine. Maybe the question is, which hydrogen are we going to substitute? How do we know which hydrogen we will substitute? So what we have to look at is that we only substitute from the poorest carbon. So the poor remains poorer in this case. Remember, in addition, we said the richest carbon that has more hydrogens will get even more hydrogen, so the richer becomes richer there. But when it comes here, we're saying the bromo will substitute from the carbon that is poorer. A poorer carbon, it means the carbon, we're saying the carbon that has lesser number of hydrogens is the one where the substitution will occur. Hence, you see the bromo is in carbon number 2. If we substitute the hydrogen in carbon number 1, we'll have a minor product. But for the major product, we'll substitute from the poorest carbon. I hope you got that. And we are saying this is halogenation. The reaction condition is sunlight. And as we move, we are having a haloalkane. In this case, it was 2-bromobutane. This haloalkane, we can use water and mild it, or we can use dilute sodium hydroxide. Don't forget, we use dilute, not concentrated sodium hydroxide. For substitution, we use dilute sodium hydroxide and mild it. And the reaction, we are referring to it as hydrolysis. Now, forgive me for not showing the bond between O and H here. Always when write OH, you must show all the bonds, even the bond between the O and the H. And then that is able to form now our alcohol, which in this case is butanol. So you are able to see that all of them, whether you use water and mild it or you use sodium hydroxide, dilute sodium hydroxide and mild it, you are able to add. And it does the same. It's going to substitute the Br in carbon number 2. Hence, we are having our alcohol with the Br and carbon number 2. If we bring HBr as well, you will be able to see that the Br can go and substitute again the OH. Then we go back to the structure that we started with. So you see that substitution, we are doing 4 types of reaction, which is the halogenation, the first one, where we use Br2 or Cl2. So that is halogenation. And we said the reaction condition, we just need sunlight. And then we said if we have a haloalkane that is formed, what we'll have to do from the haloalkane is that we simply have now to use our water and mild it, or we use dilute sodium hydroxide and mild it. And when we do that, the substitution reaction will take place. And when the substitution reaction takes place, that type of reaction where we're forming an alcohol, please learners, don't forget, we call that hydrolysis. So hydrolysis is a form of substitution. So we're able to form that, and then we are able to move forward. Now, we're just looking at the question as we go towards the conclusion of our lesson to say, as we indicated, what we have to do, just say this is unsaturated, is forming saturated. This is unsaturated, is forming saturated. So you know, we said USA. So you know that this is addition reaction, this is addition reaction, because in all of them, we're having unsaturated forming saturated. So all of them are addition reaction. But on this one, we're having a saturated forming saturated, that must be substitution. So you're able to see all those things that we're talking about. Remember what we said. We said it depends what have we added. In this case, we're having propane, which means we have added a hydrogen and a hydrogen there. We no longer have a double bond. Remember propane has no double bond. So always look at what is different between propane and the structure. So it's good that you draw the structural formula of propane, which is 3 carbons, and then you indicate all the hydrogens, and then you go and look at the 2 structures to say what is different between these 2 structures. So when you look here, you will see that, oh, we didn't have this. We had 3 carbons. This was C3. How many hydrogens? 1, 2, 3, 4, 5, 6. So it was C3H6, but this one now is a C3, but it's H8. So you can see that the number of hydrogens has increased by 2, which means that we have added H2. And when we add H2, we said it's hydrogenation. When we add H2, we said it's hydrogenation. And for hydrogenation, we said we use platinum, palladium, or nickel as our catalyst. So it becomes easier for you when you draw the structure and check what is different between those structures. 2-bromopropane, for example, you just draw the structure of 2-bromobutane, which in this case the structure will be like that. In carbon number 2, you'll have a bromo, and then you have a structure of that magnitude. So if you check here, you had a C3H6, but now you have a C3, 1, 2, 3, 4, 5, 6, 7 hydrogen. So you have a C3H7Br. What is the difference? 1 hydrogen and a Br. So you are able to say, oh, we added HBr here. So you are able to say we have added HBr there. So that is hydrohalogenation. Remember, the condition for hydrohalogenation, we said no water must be present. This one, you had a bromopropane. I told you that whenever haloalkane, you can use water and mild it, or you can use sodium hydroxide and mild it, dilute sodium hydroxide and mild it. Then you say the type of reaction that happens there, we are saying this type is hydrolysis. It's a type of substitution reaction, which is hydrolysis. You're able to do that. And if you look here, the questions will be asking about the same thing that we're doing. So I'm hoping that you have understood, and you will be able now, when you find this type of questions, you will be able to do them. As I conclude, here we are given a blue flame gas C2H2 used to cut and weld metals in the welding industry, react with excess oxygen. Remember, reaction with excess oxygen of alkanes or alkynes, hydrocarbons, when they react with excess oxygen, they form carbon dioxide and water. And the reaction is referred to as oxidation or combustion. So in this case, write down the name of the reaction referred in the above statement, because the reaction of hydrocarbon with excess oxygen, we are saying this type of reaction will be referred to as oxidation or combustion. Use molecular formula to write down a balanced equation. So you will have your C2H2 plus oxygen forming carbon dioxide plus water. I always emphasize this. As long as you know that combustion or oxidation will form carbon dioxide and water, already you have 2 marks for writing correct reactants and correct products. All you are looking for is just the 1 mark for balancing the reactions. Please ensure that you balance the reaction. You can see we have 2 carbons here, we have 1 here, so I can write a 2 there to balance the carbons. So then the carbons are balanced. We have 2 hydrogens, we have 2 hydrogens. Then you go and check for the oxygens. This side you have 2 oxygens, this side you have 2 times 2, which is 4, plus 1, which is 5. So you can see that if we write 5 over 2 here, we are going to get the right amount of oxygen. However, we don't want fractions in the balancing of equations, so you must multiply everything by 2, which will be 2C2H2 plus 5O2, forming 4 carbon dioxide plus 2 water. So you are able to check how many carbons we have. We have 4. We have 4. How many hydrogens? 2 times 2 is 4. How many hydrogens? 2 times 2 is 4. They are balanced. How many oxygens? 5 times 2 is 10. And then how many here? 4 times 2 is 8, plus 2 is 10. Then with no any doubt, you know that the reaction is balanced. And with these nice ways from Nelson Mandela, it is in your hands to create a better world for all who live in it. I'm hoping you will revise and continue to enjoy paper 2 and do well. Thank you very much. Till we meet again.